Okay. So let's just start this new chapter, which is very easy. If your aromatic compound is the concept of aromatic compound is clear, then it is very helpful for you to cover the reaction for haloarine, the chemical reaction of haloarine. Now see, we are going to start this haloalkanes. As you know, this halo stands for X, and alkanes, that is basically your R. So RH is haloalkanes or alkyl halide, and this haloarenes, that means X, and arenes for benzene. Arenes for benzene. So we are going to study about this haloalkanes and haloarenes. In this organic chapter, the topics are quite clear. Like we need to study the classification of these compounds as well as the preparation method of preparation of this compound, and then the physical properties, and then the chemical properties. This is all we need to take care in this chapter. Like the first is classification of haloalkanes and haloarenes, and this is on the basis of number of halogen atoms. This is on the basis of number of halogen atoms. Like monohaloalkane, that means one one alkane is there, one halo is there. So it is your example of monohalo. Dihalo, that means two halogen is there. That means you can either write like this, or either you can write like CHX. That means the halogen on the same atom and the halogen on the adjacent carbon. So there is geminal and there is vicinal dihalide. So can anyone tell me what is geminal dihalide and what is vicinal dihalide?
Vicinal means the halogen is connected to a carbon next to the carbon which already has halogen.
What you just said?
A halogen is connected to a carbon which is connected to another carbon which also has a halogen.
That is called
Vicinal.
vicinal. Vicinal. Okay, yeah, that's good. That means basically, if halogen is connected to adjacent carbon, that is your that is your vicinal, and if halogen is connected to the same carbon, that is your geminal dihalide or gem dihalide, and we can also call it vicinal as well. Is that clear? So this is your dihaloalkane, and then comes to the trihaloalkane, that means CH3H, and then comes your CHH, and then comes your CH3. So this is your halo group is there, so it is trihaloalkane. Can you change the slide, Krishna, Marita?
Yes, sir.
Okay.
Yes,
Then the
sir.
next, thank you. Then the next classification is on the basis of nature of CX bond, compounds containing sp3 CX bond. First of all, the nature of CX bond is polar. Why it is polar, we will discuss about it. Polarity arises due to the electronegativity difference between two atoms or two. So the first classification is the carbon which has sp3, which is sp3 hybridized, and the halogen is connected to that carbon. So you can see this is the first one is alkyl halides or haloalkanes, in which we consider 1 degree, 2 degree, or 3 degree. That means primary, secondary, tertiary. If this is the scenario, you can see how you are going to calculate the degree of halogen X. You just need to calculate the degree of the carbon to which X is connected. So you need to calculate the degree of this carbon, and how we calculate the degree of carbon. To how many carbons it is directly attached, that is called degree of carbon, and this is your 1 degree. This is your 1 degree. Since this carbon is 1 degree to which X is connected, that's why it is primary halide or 1 degree haloalkane. And in the same way, we can go for the secondary. You can see CH3, CH, and there is CH3, and then there is X, and here it is CH. No, it's okay. This is all about this. This is the scenario. Now, to calculate the degree of this halogen, you need to calculate the degree of this carbon, and this carbon is connected to 2 carbon directly. That's why it is 2 degree, and hence X is connected to 2 degree carbon. That's why it is secondary halide or secondary haloalkane. And to this 3 degree, it's very easy. 3 degree, you can see. Wait a minute, I just need to recorrect it. Now it is correct because CH2 that represents 5 bonds. That is not possible for carbon. Now come to this. What is the degree of this halogen? You need to calculate the degree of the carbon to which this halogen is connected, and this is 3 degree. That's why this is tertiary halide. Is that clear to everyone? Everyone knows about degree, how to calculate the degree of carbon as well as the degree of halogen and degree of alcohol, right? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now moving to the allylic halide, which is very important. Basically, what it is, to the carbon to which X is connected, that must be sp3 hybridized, and adjacent carbon to that sp3 hybridized carbon should be sp2 or doubly bonded. Like this will be the scenario: CH2 double bond CH, and here it comes CH2, and here it comes X. So you can see this carbon is singly bonded, that's why sp3 hybridized, and adjacent to this carbon is doubly bonded, that's why it is sp2 hybridized. Is that clear? You can also take an example. You just need to check the bond of the carbon to which X is connected, and after that you need to check the adjacent carbon, and it should be doubly bonded. So here it is not allylic part, but here it is allylic group that represents this is allylic halide. Now what is benzylic halide? Benzylic halide is also same. Only the difference is this is your benzene already, which is doubly bonded carbon, and here it will be CH2X. Now you can see to the carbon it is connected, it is sp3, and adjacent to this carbon will be sp2 hybridized or doubly bonded. So this is your benzylic halide. That is especially for benzene. Can you change the slide?
Yes, sir.
Yes, sir.
Okay. Now, as you have already studied it in class 12, sorry, right? Now, compounds containing sp2 carbon X, that means the carbon which is sp2 hybridized or doubly bonded, or you can say on doubly bonded X is connected, that is called vinylic alcohols and aryl halides. Aryl, we use aryl this term for benzene. Now, you can see vinylic halides, if the X is on doubly bonded carbon, or you can check it, it is sp2 hybridized, or you can directly write like this, like this. Now, what is aryl halide? Aryl, we use it for benzene, and you know every carbon in this benzene is sp2 hybridized, so you are going to attach X on this. Okay, so this is your aryl halides and this is your vinyl halides. Just keep this concept in your mind because it will be useful in alcohols as well. There we will call it vinylic alcohol and allylic alcohol. And here we call it vinylic halides because the group which is attached to sp2 hybridized, it is X, that's why it is vinylic halide. Okay, can I change the slide?
Yes, sir.
Now see, the nomenclature you already know. You need to take care of this. Does anyone have any doubt in nomenclature? I think you can do that nomenclature easily. Right, Krishna,
Yes, sir.
Marita, Adriel, Aditya?
Sir, can you
Yes,
explain
sir.
common names?
Common name, I will make a list and give it to you. The common name which is very, very important. Not every common name is important. Actually, we will be when we will be covering the alcohols, aldehydes, there are some common name which is very important. So we will cover that important common name there. Okay, but you have to be careful while dealing with the common name of the hydrocarbon parts like isopropyl, neopentyl. This type of these are very important. Okay.
Okay, sir.
Okay. So let's move to the next part, that is nature of CH bond. As I already told you, it is polar. Why it is polar? You know that X is more electronegative. That means the halogen is more electronegative. So it will have delta negative charge and carbon will have delta positive charge. And that's why it is polar in nature. Polar. The bond is polar. You already know that this concept you have already studied. Bond length, bond length is inversely proportional to the bond strength. If the bond length is greater, then the bond strength will be weaker. And if you are going to solve this in bond length, you know, C is common here. So we are going to decide the bond length on the basis of chlorine, chlorine, bromine, iodine size. And since iodine is the largest one, so it will have the bond length higher or the largest. Is that clear?
Yes, sir.
Now we are going to discuss about the dipole moment. Dipole moment, you have heard about this in class 12th physics as well. Mu is equal to Q into D, and you have heard of this in class 11th and 12th also in chemistry. Now, when you are going to talk about CCl4, so CCl4 has a symmetry. And when you are going to calculate the mu of this CCl4, CS2 or CDR4 or CF4, the mu will be. So always remember, when the chlorine, the number of halogen increases in alkyl part, then the dipole moment decreases. So the most dipole moment, compound in this is CH3Cl, CH2Cl, CHCl3, CHCl3, and CCl4. This is carbon tetrachloride, and this is your trichloromethane, and its common name, which is very famous, that is chloroform. And you can remember it, it's like this: CHX3, CHX3, which is very easy, important, and we call it haloform. If at the place of X you have I, that is called iodoform, and you have heard of this iodoform pair, right? And if at the place of X it is Br, then it is bromoform. So this is very important. Please do write. Can you move to the next part?
Yes, sir.
Now we are going to start this methods of preparation of haloalkane, and this preparation are very easy if you have gone through the hydrocarbon part, because every reaction in this chapter of class 12 organic chemistry, mostly the basic reactions will come from the hydrocarbon or GOC part. But here I'm going to revise all this, and it's very important. Methods of preparation of haloalkane. First, we are going to start from alcohols, and this part I have taken this from NCERT. Okay, you have seen this in your book. Alcohol react with HCl in the presence of ZnCl2, that will give you RCl plus H2O. Now see how the reaction. Generally, I do this reaction with the help of negative and positive sign, and this negative and positive sign will be decided by the difference in electronegativity. We know that hydrogen and chlorine is more electronegative, so it will have negative, hydrogen positive, oxygen negative, and this is positive. So this negative will go to positive and positive will go to negative. So this is how you will get RCl and H2O. The byproduct is not that much important in this reaction, but you can understand. You just need to remove this OH and add, you just need to substitute with the Cl of this OH. And again, OH R, then you need to do negative, positive, and Br will go. And this is how you will get RBr, ROH, CH3. You just need to remove this OH and add X, and this is how you will get H2PO. The most important reaction is these two. One of the most important reaction is, because in this reaction there are sometimes there are questions that is discussed about this byproduct. So in the alcohol in the presence of CH3, that means phosphorus trihalide, you will be getting H3PO3, that means phosphoric acid. This you will get phosphoric acid. And ROH, again replace this with Cl, and this is what you will get, POCl3, phosphorus oxychloride. And this is the next. And then ROH in the presence of red phosphorus and X2, Then again replace this OH with ROH with the SOCl2, then you will get replace this OH with Cl. And the best preparation of this haloalkane is from this, and it is because these byproducts are in gaseous state and they evolve, and you will eventually get the best product on this. Only the product that you will get, because these two byproducts are in gaseous state and they will go out. So you will get purely in this. Is that clear? Is that clear, everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Now see, this is very important reaction. The first reaction is very important reaction because HCl, concentrated HCl and ZnCl2 is basically a reagent that is Lucas reagent, and we have to study about this Lucas reagent in the next chapter, alcohols. On this, on the basis of this reagent, we can easily differentiate between 1 degree, 2 degree, and 3 degree alcohol. If you remember, do you remember it? 1 degree alcohol, no turbidity. 2 degree alcohol, you will get turbidity after few minutes. And tertiary alcohol, 3 degree alcohol, you will be getting the turbidity immediately. Is that clear? Also, it's very important to note that through this reaction, you will be getting a carbocation, the intermediate. Intermediate will be the carbocation. And whenever intermediate is carbocation, then there will be a rearrangement if possible. Rearrange if possible. Does anyone have any doubt in rearrangement? Yes or no? Can you do rearrangement easily or not? Krishna, Marita,
Yes, sir.
okay, Adriel,
Yes, sir.
Adit. Okay.
Is ring expansion also included in this?
Yes, if you know that, I'm going to give you a very short trick. There is six-membered ring, then five-membered ring, then four-membered ring, then three-membered ring. And you know that the most stable membered ring, the most stable ring is six, then five, then four, then three. Then if there is a possibility to move from three to four, then you can expand it. If there is a possibility to move from four to five, you can do that. Okay. Just remember this, the stability of the ring. Can you change the slide?
Yes, sir.
Now, the next preparation is from hydrocarbons, and we have two methods to prepare haloalkane from this hydrocarbon. The first one is from alkanes by free radical halogenation, and it's very easy. You know what free radical is? There is X. Wait a minute, Rx. Okay, I'm gonna do it like this. Let me just erase this. Instead of this, I'm gonna use CH4 and then reacting this with X2 in the presence of H nu or sunlight. Now you know what will happen. There will be free homolytic cleavage. That means basically I'm gonna write this CH3 and H. And I told you homolytic cleavage. That means it will take its own electron. Wait a minute. Both of them will take its own electron, and this is how the free radical formation took place. And then X2 also cleaved in the same manner, and you will get X. Now these electrons will be paired with each other like this, and this is what you will get, CH3X plus HS. Is that clear? Is that clear?
Yes, sir.
Now see what will happen here. Different types of hydrogen will be added with different. If I'm gonna show you, you can see that you can see easily in this reaction. You have hydrogen of this carbon. You have hydrogen of this carbon as well. You have hydrogen of this carbon as well. Let me change the color. You have hydrogen of, oh, just wait a minute, please. What I want to tell you is that you can see this carbon and this carbon will be same. This carbon will be and this carbon will be same. What I want to say, if you are going to replace one hydrogen from here, you will be getting CH3, CH2, CH2, CH2Cl. And if you are going to replace this hydrogen with a one chlorine, then you will be getting CH2Cl, CH2, CH2, CH3. That means both will have the same IUPAC. That means they are identical compound. They will be identical compound. Or if you are going to replace hydrogen from here as well as here, then it will be also same. So you will be getting two products, CH3, CH2, CH2, and then terminals carbon will be replaced by chlorine. Hydrogen will be replaced by chlorine, and then this is what you will get. You just need to replace. It's a substitution reaction. It's a substitution reaction, and then you can see it is 1-chloro-butane. You can write it, and this is your 2-chloro-butane. Can anyone tell me which one is more stable, first or second? What do you think? Which one is more stable?
Second one.
Second one is more stable because it is tertiary. You can see this will be the major product and this will be the minor. Is that clear? Is there any other product you want to draw from here? You want to produce? No, it cannot be. If you are going, I replace hydrogen from here. If you want to replace from here, you can see it will be same, 1-chloro-butane. So the product will be only 2. Is that clear? Can anyone tell me how many products you will be getting from this reaction? Cl2 in the presence of it.
One.
Only one product, because see, if you are going to replace one hydrogen from here, you will be getting this product. This is what you will get. If you are going to replace this, you will be getting this. If you are going to replace from this, you will be getting this. If you are going to replace from this, you will be getting this. And there is no hydrogen, so you cannot replace here. And if you are going to write the name of this all 4 product will have the same name. That means these are all identical compound, identical product. So only one product is there from this reaction. Okay, can I change the slide?
Yes, sir.
Okay. Now, hydrocarbon has another preparation of haloalkanes from hydrocarbon, that is from alkene, and this is your addition of H. Addition of HX can be done with the 2 methods. The first one is Markovnikov, and the second one is anti-Markovnikov. As you can see, this Markovnikov and anti-Markovnikov only will be dealing with asymmetrical alkene, not with symmetrical alkene, because in symmetrical alkene, you are going to add anyone at any place, it won't affect. Like if I'm going to show you CH2 double bond CH2, and you are going to react this with HX, then what will happen here? You are going to break the bond. Either you can add X on the left, or either you can add H on the right, or replace them like X on the right and H on the left. It won't affect because this is your symmetrical alkene. But what if you have a symmetrical alkene like propene? This is your propene, and if you are going to react this with HBr, then what will happen? There will be two possibilities. If you are going to break this, there will be 2 possibilities. X can be at the middle and H on the edge, and X can be on the edge and H can be at the middle. Are you getting my point? So there are 2 possibilities of the product. Again, you can see this is your secondary halide. That's why it is major, or this is more stable, and this will be the minor. And this reaction is known as Markovnikov. How we are going to recognize it? Whenever you are going to have an alkene reacting with HBr or HX, reacting with HBr or HX, and there is nothing written on the arrow, that means it is Markovnikov. And Markovnikov says that, you can see, this will have negative and this will have positive. This negativity and positivity that I am writing is on the basis of electron negativity. Always keep it in mind. So bromine is more electronegative, that's why there is negative charge. So according to Markovnikov, negative part of the addendum will go to that carbon which has lesser number of hydrogen, and positive part will go to that carbon which has greater number of hydrogen. And according to this, you will get this product. That's why it is measured. Is that clear? Is that clear?
Yes, sir.
Also, it is very important to note that this Markovnikov mechanism go through carbocation, formation of carbocation. There can be a question when you are going to do the Markovnikov, when you are going to apply the Markovnikov or the Markovnikov mechanism, proceed through radical carbon anion, carbocation or carbene. So carbocation will be the answer, carbocation. Is that clear? Can I change the slide? I think you have studied about this, right? You all have.
Yes, sir.
Okay. Now moving to the anti-Markovnikov, I'm gonna share here anti-Markovnikov. How you are going to recognize whether which one is Markovnikov and whether which one is anti-Markovnikov. So anti-Markovnikov will be always in the presence of peroxide. Peroxide, either it can be written like this, whole twice. So, okay. So this will be the same reactant will be in the presence of peroxide, that is anti-Markovnikov. And anti-Markovnikov says that the negative part will go to that carbon which has greater number of hydrogen, and positive part will go to that carbon which has lesser number of hydrogen. You can understand by its name, Markovnikov, anti-Markovnikov. It will be opposite. So CS3, and this is what you will get in case of anti-Markovnikov. And this anti-Markovnikov proceeds through free radical. Markovnikov proceeds through carbocation, and this anti-Markovnikov proceeds through free radical. So I think it's clear to all of you, right? Just let me know when to change the slide. Can I change the slide?
Yes, sir.
Okay, thank you. Now see, the next preparation is halogen. Wait a minute. The another preparation of haloalkene is from addition of halogens, and this is very easy. Vicinal dihalide will form. What will happen if you are going to add Br2 in the presence of CCl4 to an alkene? The bond will be broken, and this is what you will get. Bromine will be attached at adjacent position, and this is what you will get. Again, if you have like this, anything, this, and you are going to add CCl4, then you are going to write this. Whether the alkene is symmetrical or asymmetrical, it doesn't matter. Okay. So I think it's clear. Can I change the slide?
Yes, sir.
Okay. Now the next is okay. Just I had given here the anti-Markovnikov or Kraus effect. So what will be the product? You can see anti-Markovnikov has another name, that is Kraus effect, and also peroxide effect. But the work is same. The mechanism is same. You can see this is your negative, this is your positive. Negative will go to that carbon which has greater number of hydrogen. This is what anti-Markovnikov is. This is okay. After this, we have halogen exchange. Halogen exchange. This is also the method of preparation of haloalkanes. And the first one is Finkelstein reaction. The first one is Finkelstein reaction, in which we especially prepare alkyl iodide. So basically, this is your alkyl halide, where X is equal to chlorine, bromine. And if you are going to react this with NaI in the presence of dry acetone, why it is dry? Because it is quite reactive. That's why. So negative positive, negative, positive. So add this So add this negative to positive. So add this negative to positive, and you will be getting the especially alkyl iodide. And the next is so this is your Funkelstein reaction, and it is a name reaction. This is especially for the preparation of alkyl iodide. And the next reaction is Schwartz reaction, which is especially for the preparation of alkyl chloride. So we can use, you can see this is your CH3Br, and with this either we can use AgF, SbF3, COF2, Hg2F2, heavy metal fluoride. Then you will be getting CH3F along with this AgBr stress. So I think it's very easy. The chapter is very, very easy. You just need to go through the PYQs. Can I change the slide? Just let me know.
So,
Okay, everyone got the notes of GOC?
Yes, sir.
Okay. Now see the physical properties. They are colorless, sweet smell, polar. They are polar but insoluble in water. I will be discussing about this after a while. Soluble in organic solvent. Polarity RF, RCl, RBr, RI. This is the polarity order, and polarity is due to the electronegativity difference. And you know that chlorine is the most electronegative. So you can see the polarity is directly proportional to the change in electronegativity. And then boiling point, you know that boiling point is directly proportional. Always remember that. Boiling point is directly proportional to molecular weight or directly proportional to surface area. And you can also write boiling point inversely proportional to surface area, or you can write inversely proportional to the compound which has more number of branches. That means if I'm gonna ask you chloromethane, chloroethane, chloropropane, which one will have the highest boiling point? The one which is having the highest molecular mass. So chloropropane will have the highest boiling point. But what if I will ask the isomerism of the what we say pentane? Then we will have the neopentyl, which will have the most branch. Due to branching or substituent, the surface area decreases. In spite the molecular mass same, surface area decreases, and hence the boiling point decreases. Like I'm gonna explain here. This is your bromobutane, and this is also your 2-bromobutane, and this is your 2-bromo-2-methyl propane, but the molecular formula is same. So in this will have the most boiling point, then this. So highest boiling point will be A, B, C. Is that clear? Due to branching, its surface area decreases. That's why its boiling point also decreases. Is that clear?
Yes, sir.
Okay. So in class 12 solution chapter, you have studied about the principle of solubility. That means basically like dissolves in like. That means polar solute will be dissolvable or soluble in polar solvent, and non-polar solute in non-polar solvent. But here you can see polar. They are polar. CH3H is polar. As I told you, there will be delta negative, delta positive. And H2O is also polar. H2O is also polar, delta positive, delta negative, delta positive, delta negative. But they are not soluble in water because there will be no hydrogen bonding. That's why, in spite they are polar, but they are not dissolvable or soluble in water. These are very important points regarding physical properties, and I think it's clear, right?
Yes, sir.
Okay, I'm going to change the slide. Okay, the next preparation of halorine. It's very easy. See, first of all, what you need to take care of is Fe, Cl3, or if you have Fe and you are going to add X2 in this, you know what will happen? There will be, due to this reaction between these reagents, there will be generation of an electrophile. And this electrophile will be attacking on which position? either it will attack on ortho, or either it will attack on para. Yes or no? Please do let me know. This will be the product.
Yes, sir.
So this is how you will prepare the haloarine, and this will be your major and this will be your minor. The reagents are very important, and you need to recognize which type of nucleophile or electrophile they will be generating. And this reaction is basically electrophilic substitution reaction, since it is written here. So this reaction will be generating electrophile. And with the addition of this X2 in the presence of iron, you will be getting X plus. Is that clear? Please do write it. Can you change the slide?
Yes, sir.
Yes, sir.
Thank you. Next. The next one is amines from amines by Steinmer's reaction. I think you have already studied about this as well, because you have studied amines as well. So there were the chemical reaction of amines, this, and then this is the preparation of haloalkane. You know what will happen here when aniline will be reacting with nitrous acid NaNO2 in the presence of HX. So what will happen? There will be formation of a benzene diazonium chloride. I'm going to take HCl here. So it will be benzene diazonium chloride. So here it will be N2 plus plus X minus, which is, or you can either write N2 as a whole. I'm going to write it N triple bond N and negative, and here it is positive. So this will be your benzene diazonium. Since I took HCl, so I'm going to write it benzene diazonium chloride. This is your benzene diazonium chloride. After getting benzene diazonium chloride, what you need to do? It's very simple. N2 plus X minus, you are going to pass it to U2X2, and you will be getting what? You will be getting X. You will be getting X here, and N2 will be released. So this is how we prepare haloarine from amine. And this reaction is Steinmer's reaction. Please do write it. Can I change the slide? Please do respond.
Yes, sir.
Okay. The next part is optical isomerism. Can you anyone tell me, are you aware of this? Are you aware of this optical isomerism? Yes or no? Please do let me know.
Sir.
Yes, sir.
See, it's very easy. Do you know how to calculate chirality or chiral carbon? Yes or no?
Yes, sir.
Yes, sir.
Okay, what is chiral carbon? The carbon which is sp3 hybridized and surrounded by 4 different groups, that is called your chirality, like the way I wrote it here. You can see this is sp3 first. You need to check the hybridization sp3 it is, and then you need to see the group to which it is attached. And if it is different, and hence here it is different, and that's why it is chiral carbon. That means this carbon is chiral. So what is a stereoisomer? First of all, the compounds which cannot be superimposed on each other. The compounds which cannot be superimposed on each other due to chirality are known as optical isomers. And these compounds which are not superimposable on each other, they are also known as enantiomer. Remember, the compounds which are not superimposable to each other, that is called enantiomer. Is that clear?
Yes, sir.
And since
Yes,
they are
sir.
not superimposable, that means they are optically active. If you want to check whether a compound is optically active and not, then take a mirror image of that compound and then superimpose them. If they are going to superimpose on each other, that means that is optically inactive. And if they are not superimposable to each other, that means they are optically active. And there is another way. By experiment, we can easily define whether it is a whether it is optically active or not. So you need to pass these substances, the substance which poses the property to rotate the plane polarized light. Basically, if you have a compound and you don't have any idea about its optical activity or inactivity, you just need to pass a light through that substance. That light is plane polarized light. That light is plane polarized light. And if the light will rotate either clockwise or anti-clockwise, if it will rotate, it is optically active compound. Now see, if it will rotate clockwise, it is known as D or plus. That means dextro-rotatory. And if it will rotate anti-clockwise or counterclockwise, you can say anti-clockwise, then it is denoted by L and or negative, and this will be levorotatory. Is that clear? Levorotatory. These are very important. Clockwise, dextrorotatory, positive. Anti-clockwise, levorotatory, negative. And if there is no rotation, that means it is optically inactive. Is that clear?
Yes, sir.
Yes, sir.
Okay, I'm gonna change it. Okay, I'm gonna give some questions about chirality. Or just check, let me know which one is chiral and which one is chiral. Please do it.
So what is D and T in the sixth?
Yes, are you talking about D? D, deuterium, isotopes of hydrogen, and this is your tritium. Okay, who has the message? MJ, MJ. Okay. Very good, Marita. Very good. Tasty, very good. Well painting. One chiral and six chiral. Very good. Very good. You can check this carbon, different group and hydrogen. So it is chiral. If you are going to check this, this is also chiral. But if you are going to check this is different. This is also different. But this is OH and this CH3OH, 3H2OH is not. That's why it is not. In the same way, this is also not. This and this is similar. That's why it is also not chiral. And if you are going to check about this is your sp2 hybridization. So you are not going to check. Okay. Everyone clear about it?
Double bonds, should we consider that carbon is bonded to the same atom twice? Should we not
Wait.
consider?
Marita, are you saying that? See, This is the first carbon, this is the second carbon, which is doubly bonded to this, and then this. This is the scenario. Marita, can you repeat your question?
Yes. So if we have a double bond, should we consider that that atom is bonded twice to the same group? So
Yeah,
it will not
it
be
is.
chiral.
Yeah, it will not be chiral because it is a sp2 hybridization. For chirality, it is should be sp3 and 4 different groups. Okay.
Okay, sir.
Okay. One more question from
Sir, can you
yeah.
explain the fourth case?
Which one?
Fourth one.
Fourth one. Fourth one, you can see this is your hydrogen. This is your hydrogen. So two both same group on this carbon. So it is not chiral. Come to this. This is your chlorine. This is your hydrogen. Two different groups, but this part is similar. The other two group is same. That's why it is not chiral. Is that clear, or I should explain it more?
Understood, sir.
Is there any other doubt? Okay, I'm gonna ask you a question.
So, sir, we should call the fourth one not chiral, right?
Which one? Yeah, it is not chiral. This is not chiral. Only the chiral is first and sixth. Adriel, I have sent the note. Have anyone got the note? GOC.
Yes, I have
Basically,
got.
yeah, I sent the this one note in PDF form. That was some part will be written and some part will not be written. But today I will try to extract in the same form. I tried but failed. Okay.
Sir, I have not received it.
Okay, you will be receiving. Okay,
thank you.
I'm gonna okay, thank you. I'm gonna start this inversion, retention, and racemization. This is very easy. This is very easy. First of all, I wanna ask you a question. Do you know what is inversion? Inversion is basically if I'm going to react, I'm gonna write a question. See, this is your scenario C2H5. And this is your chiral. This should be chiral, and this is your X or Cl. I'm gonna take. If the reaction proceed like this, now wait a minute. I'm gonna react this with the nucleus, and I'm gonna react this with the nucleus. Okay. Let's see what will happen. There are two possibilities. This will move in this direction, and chlorine will attack. Nucleophile will attack on this, and nucleophile just replaced at the place of Cl, where the Cl was initially, and there is another probability that it will come in opposite direction or opposite configuration. What I want to tell you is that if the reagent that is attacking will be at the same place of the chlorine, that is called your retention. That is called your retention of configuration. And if nucleophile will be opposite to that chlorine that it is going to substitute like this, that is called inversion of configuration. Inversion of configuration. Is that clear to everyone?
Yes, sir.
And if you are going to do the reaction, it is possible in some type of reaction, that is SN1, that it can either do this or do this. That means I'm going to take this A as A and this as B. And if you are going to get the same product, A plus B, with a 50% and 50%, this is known as racemic mix. Racemic mix. And this racemic mixture is basically the process is known as racemization. So if you remember, in SN1, you will be getting racemization or racemic mixture. And in SN2, you will be getting only inversion of configuration, because in SN2, back attack is possible only. Only the back attack is possible. That's why you will be getting inversion of configuration in SN2. That means basically, if the reactant will have a configuration of L levorotatory anti-clockwise, the product will be in dextrorotatory. The product will have dextrorotatory. But in SN2, you will be getting this as well as this. That means clockwise, anti-clockwise. That means net rotation here will be 0, because you will be getting the both the product in equal amount, and half of the product will move anti-clockwise and half of the product will rotate, basically not move. Half of the product will rotate the plane polarized light clockwise, and half of the product will rotate plane polarized light in anti-clockwise. So both will cancel, and net rotation will be 0. Is that clear?
Yes, sir.
Okay.
Sir, can you explain the SN2 and SN3?
Yeah. I'm coming on that. Okay, don't worry. we have to study. I just since you have studied class 12 a few days ago or a month ago, that's why I just took that name. We will be studying about SN1 and SN2. Now here you can see. Now we are we are done with the physical properties. We are done with the preparation. We are done with the nomenclature, classification. Now this is your chemical reaction. Now chemical reaction in this chapter is of 3 types: nucleophilic substitution reaction, and here the nucleophilic substitution reaction is of 2 types, SN1 and SN2. What it is, we will discuss about this. Then elimination reaction, and this reaction is also known as beta elimination reaction. And then comes your reaction with metals, in which we will talk about Woods reaction, fatigue reaction, Woods fatigue reaction, and also reaction with Grignard. So let's start this nucleophilic substitution reaction. What is nucleophilic substitution reaction? Basically, you can see in the name it is nucleophilic. That means nucleophile will attack. So this is your Rx. So X will take electron from R. So there will be positive charge, and this nucleophile will attack on this R, and nucleophile substituted. And this is what the reaction is known as nucleophilic substitution reaction. Now, I have taken a lot of example of this with which we can easily understand. This reaction, I'm going to teach you in a way of negative and positive. Now, you can see this will have negative, this will have positive. This will have positive, this will have negative. So the negative will attack here, and you will be getting ROH, alcohol. You can see H2O has 2 parts, H plus and OH minus. Again, this negative will attack on R, and you will be getting alcohol. You know that this is sodium, so it will have positive, and oxygen has negative. Again, this will attack on this. This will be the nucleophile. This will be the nucleophile. This will be the nucleophile, and you will be getting ether. Again, you can see negative, positive. This is the nucleophile that will be attacking R, and you will be getting alkyl iodide. This is NH3, in which I can write HNH2, and hydrogen will have positive, and this will have negative. And this is how you will get 1 degree amine. This is how you will get 1 degree amine. Then R dash NH. So can I write R dash NH2 as like this? This is positive, this is negative. Again, this will attack on this, and you will be getting 2 degree amine. And again, you will be getting 3 degree amine. 3 degree amine by replacing that hydrogen. Hydrogen will have positive, this will have negative, and this negative will be attacking in this. Is that clear to everyone? The reaction in organic chemistry is very, very easy if you will go through the rule, and only the problem comes when the reagent is going to work. So we are going to give our 100% to this reagent. What its main work, what it is, basically oxidizing agent, reducing agent, or whatever is its function. Now the next reaction is very important, that is KCN, and you can see this is your negative that will be attacking, and this is also your negative that will be attacking. But here you can see This is your RCN and this is your RNC. Why it is so? It's very important. See, here it is your RX. I'm gonna react this with KCN. KCN can I write K plus CN minus. Why I wrote it so? Since KCN is purely ionic compound, so CN will be like this and nitrogen will have a lone pair. So this will move. Now in CN, two donor site is there. Two wants to go to the positive because this is negative charge, this is lone pair, but negative charge acts more, or negative charge is more, have more nucleophilicity than a lone pair. That's why carbon will make bond with RC. But when you are going to talk about this AgCN, AgCN is more covalent. That means basically it is a covalent bond. So there will be no charge on carbon, but there is a lone pair on this nitrogen. So it will go on this. And that's why it becomes RNC, isocyanide. Due to this covalent character of AgCN, there is no negative charge on carbon. That's why it forms isocyanide. And since KCN is a ionic compound, so there is a lone pair along with negative charge. That's why this negative charge attack on R, and this is cyanide or nitrite. This is important. Is that clear, everyone?
Yes, sir.
I'm moving to the next. Now, this is also the same. You can see this is negative, this is positive, this negative will go, and you will be getting alkyl nitrite, AgNO2. This AgNO2 again, this AgNO2 again the covalent character. So this will attack from here, and you will not attack from here. Wait a minute. Let me show you. KNO2, RX is there. KNO2 will be like this. K plus because it is ionic. O and double bond O, and there is negative. So it will attack on that easily. It will attack on that. Nitrogen has a lone pair. That is good. But this negative charge has more nucleophilicity than a lone pair. So it will be like this. But when we are going to talk about this AgNO2, when we are going to talk about this AgNO2, you can see there is no negative charge. Only the option left is nitrogen, so it will attack on that. That's why nitroalkane forms. So this two reaction is very important, and the rest is as it is very easy. This is negative, this is positive, so this negative will be attacking on this, and this is how you will get ester. Lithium aluminum hydride is the very best reducing agent, a strong reducing agent. R M, R dash M, this R dash M, you know that. Wait a minute. R dash M. You can see M is metal, so this will have negative and this will have positive, so it will attack on this, and this is R dash. You will get. So we also did some reaction from the onwards chapter, like alcohol. We prepared alcohol as well, nitroalkane, ester is here, hydrocarbon is here. So it's all are very important, and they are all connected to each other. Can I change the slide?
Yes, sir.
Yes, sir.
Okay, thank you. Now, there are two types of nucleophilic substitution reaction. As I told you, I'm going to give you again the example. This will move in this, and this will be attacking on this. So this will be the product that you will get, and this is known as nucleophilic substitution reaction. It is of two types, SN1 and SN2. This is basically unimolecular nucleophilic substitution reaction. And this SN2 is basically bimolecular nucleophilic substitution reaction. You have heard about this statement or this sentence. What I want to say, unimolecularity and bimolecularity in chemical kinetics, right? Unimolecular, that means the reacting species is single, and bimolecular, that means reacting species is double. Now, you can see unimolecular, I'm gonna show you. See, this unimolecular proceeds through two steps. In the first step, it is proceeding. This is your basically formation of carbocation. X minus will X. Wait a minute, please. Abruptly, sometimes it closes. Now see what I want to say. X is living group, so it will be out. So there will be positive charge and R1, and then there is R2, and then there is R, and X will be out. So this is the first step, and this first step is slow step, and that's why it is RDS, rate determining step. Why it is slow? Because it is more stable here, it is less stable here. That's why it is slow. After this, in the second step, you can see R1, R2, and R3 will be reacting with the nucleophile. And it's very important to note here that nucleophile can attack from front and nucleophile can attack from back as well. It will not affect it because there is a formation of carbocation. So if it will attack from, wait a minute. Okay. If it will attack from front side, then it will replace the position of X where it was earlier. That means you will be getting this product. You will be getting this as a product. R2 is here and R. And if it will attack from back side, this is the back and this is front attack. So in this condition, nucleophile will be opposite of the chlorine or X. Sorry, X. So basically in SN1, both possibilities there. Nucleophile can attack from front as well as nucleophile can attack from back side because there is a formation of carbocation. And here you can see front and back. That's why racemic mixture will be there and racemization will be. Net rotation will be 0. Please do write it, or if you are done with this, just let me. The reaction is two-step. The first two-step reaction. First step is RDS, rate determining step. Since in the first step only one molecule is involved, that's why it is unimolecular. And also the order of reaction is 1, as rate is equal to, or rate directly proportional to RH, and it has a power 1. Only in RDS, rate determining step, only one reactant is there and there has a power 1. That's why SN1 is first order. Is that clear?
Yes, sir.
Okay. Now, reactivity. When we are going to talk about reactivity, so reactivity in SN1 directly proportional to, since formation of carbocation took place, so stability of carbocation, and we know that stability of carbocation is 3-degree alkyl halide, then 2-degree, then 2-degree alkyl halide, then 1-degree alkyl halide, then CH3, then CH3. Then comes your next about living group. So living group, you know that Ri greater than RBr, greater than RCl, greater than Ra. So basically, the bond which is lengthier will be easily releasing itself. That's why Ri, RBr, RCl, Ra. So there are a lot of questions on the basis of reactivity towards SN1 and SN2. We will discuss about it. SN2 also. For SN2, it is 3-degree, 2-degree, 1-degree, and if degree is same, then iodide, bromide, chloride, and fluoride. Is that clear?
Yes, sir.
Okay. Can I change the slide?
Yes, sir.
Yes, sir.
Now I have written here the same thing that I told you. Characteristic of reaction: unimolecular, two-step reaction. First step, living group leaves. That means X minus. In second step, nucleophile attack. First order reaction it is, and racemization. Okay. So this was the SN1. Then factors affecting SN1, you can see 3 degree, 2 degree, 1 degree, CH3H, RI, RBR, RCL, if living group, if we are going to talk about living group, then nucleophile does not affect. Nucleophile does not affect it. Okay. And also it will be favorable in polar solvent. Polar solvent. Okay. And racemization. Okay. Then come for the second, that is SN2, that means bimolecular nucleophilic substitution reaction. In bimolecular nucleophilic substitution reaction, see what will happen. Basically, it is a single step reaction. Single step reaction, that means if this will release itself, at the same time, this nucleophile is gonna react with this. That means make bond with this. But this way is not possible because you know that when X will take electron from carbon, there will be negative charge, and they will be coming in each other's way, and they will be replacing repulsion. There will be repulsion between these two because nucleophile has also negative charge, and this X minus has also negative charge. So what will happen? So nucleophile will go backside, and then it will attack. Then it will attack. Let me show you the reaction. First of all, SN1 is in two steps. First, the nucleophile leaves and First, the X minus leaves. Nucleophile will wait until X minus leaves. But here in SN2, nucleophile does not wait. X minus while leaving the alkyl group, nucleophile will attack. So see what will happen. So this will be the scenario. Wait a minute. I'm gonna read from because this I wrote it wrong. So I'm gonna show you from. So see what will happen. This is carbon. The X bond between carbon and X is about to break. Then nucleophile will attack, and there will be a scenario to the formation of bond between carbon and X. And R is there as usual, and H is there, and this is your transition. This is your transition. Okay. And after this, what will happen? You will see. See is there. Nucleophile will be attached opposite to the X. Wherever X was, nucleophile is attached opposite to the X. H is here and D is here. And you can see, I told you what is inversion. If the living group will leave and coming group will be attaching at the same place, that is retention. And if the attaching group will be opposite to that living group, that is inversion of configuration. Inversion of configuration. Is that clear, everyone? Is that clear?
Yes, sir.
Now see, as you understood why the front attack is not possible in SN2, because here the bond breaking and the bond formation taking place at the same time. In case of SN1, bond breaking took place, and after a while, then bond formation started. That's why their front attack as well as back attack both were possible, but here it is front attack is not possible. Now, if I'm gonna ask you a simple question, since we are talking about SN2, so here is the SN. And you know that in SN2, only back attack is possible. Only back attack is possible. So can anyone tell me? Can anyone tell me? So which alkyl halide nucleophile can easily attack? A, B, or C, or D? In which this is your A, this is your B, this is your C, this is your D. in which nucleophile can easily attach? Can easily attach.
D.
B or D?
D.
B for book, Bombay.
D. No. B. D.
D for dog.
D for dog. Okay. So your answer is D. That is correct. Because while attacking this carbon by the nucleophile, there will be a steric hindrance, and that's why in 3-degree carbon or 3-degree alkyl halide, for nucleophile it is tough to attack. In the same way, this is your 2-degree, this is your 1-degree, and this is your super primary. That means what I want to tell you is that if you are going to do the reactivity, of SN2, then it is CH3X, that is super primary, then 1-degree, then 2-degree, then 3-degree. Leaving group will be as it is in the same way as we did for SN2, but 1-degree, 2-degree, 3-degree will be, this will be the order for reactivity towards SN2. Is that clear? Can I change the slide? Marita, Krishna.
Yes.
So this is what I have written here, characteristics of a reaction. It is bimolecular. Bimolecular, why it is bimolecular? Nucleophile and alkyl halide both are acting simultaneously. In case of SN2, only alkyl halide was there. That's why it is unimolecular. Also, second order reaction, because power 1 plus. There was only alkyl halide which has a power 1. That's why first order. Inversion of configuration takes place. If carbon is chiral, this is also very important. If carbon is not chiral, then you won't be able to write it in version of configuration taking place. Chiral is carbon, then inversion of configuration is taking place, and this is in our syllabus. Chiral will be asking. Okay. Now, factors affecting rate of reaction. You can see super primary, 1-degree, 2-degree, 3-degree. For SN2, leaving group same. Also, it's very important to note that polar protic solvent favors SN2 reaction. There are two types of polar, that is polar protic. The first one is polar protic, and the second one is polar aprotic. Polar aprotic. Now see, if there will be a question which will be faster in SN1 or SN2, you can easily decide it by looking at the degree of alkyl halide. But if the nucleophile is different, then what will happen? Or solvent is different. So there is a polar protic solvent. Polar protic solvent is what? The solvent in which hydrogen is directly attached to phone. That means hydrogen is either attached to fluorine, oxygen, nitrogen. That means H2O, NH3, HF. These are all types of polar protic solvent. You can take carboxylic acid as well because hydrogen is directly attached to oxygen. Polar aprotic solvent, that means the solvent in which hydrogen is not directly attached to oxygen or fluorine or nitrogen. You can see these hydrogen are attached to carbon. These hydrogen are attached to carbon. So the solvent in which hydrogen is not directly attached to either fluorine, oxygen, or nitrogen, that is aprotic solvent. Is that clear? Can I change the slide?
Yes, sir.
Also, this is also important. Anionic nucleophile generally gives. Now, the next reaction, we have only 2 reactions left, so we are going to complete this. Elimination reaction, dehydrohalogenation reaction. First of all, halogen atoms having beta hydrogen atom undergoes beta elimination. What is beta hydrogen? So I'm going to discuss about it. You can see the carbon to which X is connected, that is your alpha, and the carbon which are directly attached to this alpha carbon, that is beta. Okay, that is beta. And the hydrogen which are directly attached with beta carbon, that is beta hydrogen. Are you getting my point? Simple. What is alpha carbon? To which X is connected? The carbon which is directly connected to X or halogen, that is alpha carbon. And the carbon which is directly connected to alpha carbon, that is called beta carbon. And the hydrogen which is connected with this beta carbon, that is called beta hydrogen. And what you are going to do, this is will be in the presence of either alcoholic KOH or alcoholic NaNH2 or KNH2. What will happen? This you are going to remove. And what will happen? Two bond will be left here. Two bond will be left here. Single bond was there. Now there will be double. You know how the reaction took place? It's very easy. This will leave first. So there will be negative charge. There will be positive charge. There will be, because it will take electron from carbon. And this carbon, what this carbon will do? This will take hydrogen's electron and make double bond. So this will be living in the form of X negative, and this hydrogen will be living in the form of H plus, and there is a OH minus that is waiting. So it will take with, and it will form H. Is that clear? So we don't need to deal with the byproduct. We need to deal with the main product. So what you need to do, you just need to remove different types of beta hydrogen and X together. They will be adjacent to each other and make double bond with them, between them. Is that clear?
Yes.
Can I change the slide?
Yes.
Okay. Now I'm gonna give you a question. Okay, please do this. You just need to find the beta carbon, beta hydrogen. Only one product will be there, Marita. Okay, I'm gonna show you major. Very good. Two products will be there. You just need to see, this is your alpha, this is your beta. Very good, Krishna. Okay, and this is your beta. So first I'm going to take this. So you are going to remove this bromine and this hydrogen. So what will be the product? This will be as it is, and there will be CH, double bond CH. And then you are going to remove this. So there will be CH3, and then comes your CH, double bond CH, and this will be your CH. So this will be your but1 but2 and this will be your but1. So this will be your minor, and this will be your major, and this product is also known as Sedgwick. Sedgwick will be always major in this, because it says that more alkylated part will be there. You can see two alkyl parts, and here only one alkyl part. So this will be major, and the above one is minor. Is that clear? Okay. Can I?
Yes, sir.
Okay. The reactivity that I am given here, just write it, and I'm going to give you a very good question. Very good. Very good question. This is your solid. Please do it. I'll be coming in a one. Just need to take water. Everyone done with this? Okay, you cannot write the name because I will not be. Yeah. Okay, very good. The hydrogen is projected outward, will be removed. Okay, outward that means wedge, right?
Yes, sir.
Why it is so?
So repulsion between bromine and hydrogen.
See, it is anti-elimination. Anti-elimination. Anti-elimination that means this bromine and this hydrogen. This is solid and this is wedge. So this will be removed and the double bond will be taking place at this. Okay, and this will be as it is. So anti-elimination, if the that is good, Marita. If the questions come in 3D, you need to remember that this is your anti-elimination. There are some reactions that will be specified by syn addition, anti-addition. Anti-addition that means it will be addition takes place in different configuration. One outward, another inward. Is that clear? Can I change the slide?
Yes, sir.
Sir, could you please tell about anti-elimination?
Anti-elimination is see the you need to remove. You know that alcoholic KOH. This is your beta elimination. This is your beta elimination. But you have to take care when the question will be in 3D like this. If the question will be in 2D, you can remove the way you did in this question. But if it is given in 3D, so if Br is on solid wedge, you are going to remove that hydrogen, which is dashed wedge. Are you getting my point, Marita? If one is
Yes, sir.
outward, you are going to remove. If you are going to remove the bromine from inward, then you are going to remove the hydrogen from outward. That is anti. Okay. If the question is in 2D like this, you can remove any one of them. It won't happen. So can I
Okay,
change
sir.
this? Very good. Thank you. Can I move to the next part? Everyone done with this? Okay.
Yes, sir.
Thank you. Chemical properties of haloarine. You have seen that haloalkane easily reacted towards nucleophilic substitution reaction. But when we are going to talk about aryl halides, these are extremely less reactive towards nucleophilic substitution reaction. Extremely less reactive towards nucleophilic substitution reaction. Towards nucleophilic substitution reaction. Okay. So the first reason is a resonance effect. The first reason is resonance effect. The second reason is difference in hybridization. And the third reason is instability of phenyl instability of phenyl cation. What I want to say is that, see, there is a chlorobenzene and there is a chloroalkane or chloromethane. Let me make it clear. So as you know that to do nucleophilic substitution reaction, you need to break this bond as well as this bond. In haloalkane this and in haloarine this. But it is easy to break this bond as compared to this because this has partial double bond character due to resonance. Isn't it? Due to resonance, this PCl bond is partially double bond character containing. Yes or no? Please do respond.
Yes, sir.
Yes, sir.
And if you are somehow, if you are going to break this chlorine, there will be positive charge on double bond, which is very, very less stable, highly unstable it is. And then also this is your sp2 hybridization and this is your sp3 hybridization. This can be easily convertible into carbocation as compared to this. So these are three main reasons. That's why the nucleophilic substitution reaction does not favor haloarine. Still, if you want to carry that reaction, you have to give a very drastic condition like very high temperature, very high pressure. Okay, in the in the way you can see, you have seen this reaction. If you have this benzene, and this is basically your chlorobenzene, and if you want to do the nucleophilic substitution reaction, that means you are going to react this with NaOH with a nucleophile. So this reaction will be only taking place at 623 Kelvin, very high temperature. Wait a minute. Let me know when you are able to see this. Okay. 623 Kelvin and then 300 atm pressure followed by H plus. Then you will be getting alcohol, that is phenol, not alcohol. This is your phenol. So from this reaction or this condition, you can easily understand how tough is to carry a nucleophilic substitution reaction towards basically to this haloarine. But if you want to carry this reaction as a little earlier or faster than the previous one, first of all, this reaction is known as Dawes process. Dawes process. Now, if you want to carry this reaction faster, then what you need to do, just make this chlorobenzene reactive. And how it is possible? If you are going to put a minus M effect group, that means basically this NO2 has a tendency to withdraw electrons and it will decrease electron density in the benzene ring and hence increases its reactivity So if its reactivity increases, that means somehow its condition decreases, and with substitution of one NO2, you can see the temperature decreases to 443 Kelvin, followed by H plus or STD, and you will be getting the nitrophenol. And if you want to make it more reactive, then you are going to add 2 NO2 group. This is your second NO2, and the first NO2 was there. So again, NaOH 443 Kelvin and H2, and you will be getting This will be replaced by OH and NO. And the last reaction is very important. That will be done only with the help of warm water, and that is NO2. NO2, not here. This is your meta position. Chlorine NO2 at para and NO2, sorry, hot. So you just need to, this will be very, very reactive. If you are going to pass this to warm water, then it will be converted into, you can see, 2, 4, 6 trinitrophenol, and its common name, that is very important, that is citric acid. So this is how we increase the rate of reaction of the chlorobenzene or halorine towards nucleophilic substitution reaction. Is that clear?
Yes, sir.
Yes, sir.
Okay, can I change the slide?
Yes, sir.
So everyone knows that in aromatic hydrocarbon, we have studied when an electrophile generated, we are going to study about basically the electrophilic substitution reaction. Electrophilic substitution reaction. Aromatic electrophilic substitution reaction. So only you need to take care is that if you remember in the previous class, I told you electrophile will be substituted at any position. If there is only benzene, let me show you. Yeah, here it is. Where it is? Yeah, if there is only benzene, you can see. If there is only benzene, then electrophile can be added anywhere. So you just need to remember. Can you see the screen? Yes or no? Are you able to see
Yes,
the
sir.
screen?
Yes,
So this
sir.
is your benzene. If concentrated HNO3, concentrated H2SO4 will be mixed together and heat, then with the help of this reagent, we will be getting an electrophile NO2 plus, and this will attack on benzene at any position. But when you have something group already some group on this, that means CH3 is there, and you will be generating the same, but with respect to CH3, you will be getting two products, ortho and para, because this CH3 has plus H or plus I effect. If this CH3 will be minus N, not this CH3, at the place of this CH3, there is some group like NO2 already, that is minus M affecting, that is para directing. We also discussed about this, if you remember. So I'm going to show you on the main chapter, you will be able to understand. So first of all, I'm not going to write all the reactions, but I'm going to remind you, this is your halogenation. I'm going to write the name of all the electrophilic substitution reactions. Then comes your nitration. Then comes your sulfonation. How the sulfonation will take place, and you will be able to do the recipe. Then comes your Friedel, Kraft, alkylation reaction. Friedel, Kraft, alkylation reaction. Yeah. Okay. So see, here is your halogenation, and how halogenation will take place. If you are going to take Lewis acid plus X2, if you are going to take Lewis acid plus X2, Lewis acid, like either you can take AlCl3 or either you can take FeCl3. FeCl3. So with this combination of reagent, you will be getting an electrophile that is X plus. That is X plus. Are you getting my point? Yes or no? Are you
Yes,
getting
sir.
my point?
Yes, sir.
or either since I am using Cl, so there will be Cl. So you can see I'm going to write a reaction here. So if you have a chlorobenzene, since we are studying the chemical reaction of haloarine, and you are going to react this with X2 in the presence of, let me take Cl2 in the presence of either AlCl3 or either you can take FeCl3, and this should be anhydrous. Then what will happen? There will be generation of Cl plus, and this Cl plus will be attacking either on ortho and either on para. So what you need to do with respect to this chlorine that is already attached, with respect to that, you need to add the electrophile at ortho and para. Since there will be a steric hindrance, this will be your major product and this will be your minor. Is that clear?
Yes, sir.
Everyone.
Yes.
Now see, in nitration, what very good. Now see, in nitration, what we use? We use concentrated HNO3 plus we use concentrated H2SO4 and we heat it. Then we get an electrophile that is NO2 plus. Again, you have this chlorobenzene and you are going to react this with this, and then you are going to, with the combination of this, you will be getting an electrophile this, and you are going to add this NO2 at ortho and para, and you will be getting the nitration result. Is that clear?
Yes, sir.
For sulfonation, you are going to either add concentrated H2SO4 fuming or plus SO3 you can take, or either you can take oleum. So from this, you will be either getting SO3 neutral electrophile or either you will be getting SO3H plus. And this will be adding to this chlorobenzene with this respect, with respect to chloro in this benzene, you are going to add this SO3H to ortho and para. And then comes your Friedel-Crafts alkylation. Then comes your Friedel-Crafts alkylation. For alkylation, what you need to do, Rx in the presence of AlCl3, or either you can, so there will be generation of again R plus, there will be generation of R plus, or either you can say RCl plus AlCl3. So there will be generation of R plus, and this R plus will be adding on chlorobenzene at the place of ortho and para. The last electrophilic substitution reaction is Friedel-Crafts acylation. So this reaction is also very easy. You need to take an acyl halide in the presence of anhydride AlCl3. In the presence of anhydride, in this case AlCl3 will always be in anhydrous form. Anhydride AlCl3, and with this reagent you will be getting an electrophile that is RC double bond O positive. So I'm going to explain this reaction, the last one, which is very easy also. If you have a chlorobenzene and you are going to react this, if you have a chlorobenzene and if you are going to react this with, let me take R as a CH3, C double bond O and Cl, and then another is anhydride AlCl3. So what will happen here? You know that there will be formation of this positive, this will go. So this will be attacking directly on ortho as well as para. So what will happen here? You can easily see. First, it will form C double bond O CH, which is ketone ortho. Friedel-Crafts acylation takes place, and then C double bond O, and then CH, and then here it is CH. So it's very easy. Isn't it easy? Can't you do the rest one? Alkylation, sulfonation, and nitration. You can do that.
Yes, sir.
Can I change the slide?
Yes, sir.
Okay. So everyone is aware of this now. Now come to the next. That is basically reaction with metal, and this is your last reaction of metal. And in this, we have the first reaction with sodium. Reaction. Reaction stands for reaction with sodium in the presence of dry Sodium in the presence of rice. So if you have Rx and you are going to react this with Na in the presence of dry ether, I'm going to write it B. You need to take 2 ml of this and just double it and make a bond with each other. This is what you will get, and 2Na. You have already studied about this. You can either remember like this, 2Na, and I'm going to write another mole of this Rx in inverse or mirror image of this, and then I'm going to take it out and you will be getting this R. Is that clear? This is known as Wood's reaction. This is known as Wood's reaction. Is that clear?
Yes, sir.
The next reaction with chemical. The next reaction with chemical is known as Fittig reaction, and R here is for alkyl. But if you are going to take aryl, what will happen? This is also in the presence of dry ether. You will be getting AR. That means biphenyl. That means you will be getting bi. And this reaction is known as Fittig reaction. This is known as Fittig. And the last one is quite easy. That is Rx plus Na, 2Na, and H benzene in the presence of dry ether. So this will be your Wood's Fittig reaction. This will be your Wood's Fittig reaction. When you are going to fuse an alkyl halide and aryl halide, that is your Wood's Fittig reaction. Is that clear?
Yes, sir.
Okay. Are you done with this?
Yes, sir.
Okay. The next is Grignard reagent. Grignard reagent. What is this Grignard reagent? Before this Grignard reagent, we have a name or a term that is organometallic compound. Organometallic compound. Organometallic compound, that means the bond between carbon and metal, that is called organometallic compound, and this Grignard reagent is one of the organometallic compound. If you are going to react this Rx with Mg, you will be getting RMgH, and this is what we call Grignard reagent. There is a bond between carbon and magnesium, that means metal, and that's why it is also called organometallic compound, and this is very, very reactive. This is very, very reactive. If you are going to, it is so reactive that if we are going to pass this, or if it will touch in any condition, if it will go through moisture, H2O, that means H plus and OH minus, it will convert itself into hydrocarbon. Like this has a positive, this has a negative. So this negative will be going with this. So it will be converting into hydrocarbon, and the byproduct will be there. Please do write it. Let me know when you are done with this.
Done, sir.
Done, everyone?
Yes, sir.
Yes, sir.
Very good. So this was the concept of this chapter. Basically, it's very easy. Now we need to do the PYQs. So I had added very less questions, only 2 questions and some questions somewhere else. So please do this first. Very good. Sanjay. Uh, is there any answer from any other one? Dilute KOH and iodoform is KIO. Krishna, any answer from you? Oh, no, no, no. See, C3H6. First of all, it is an alkene. You can see this is your an alkene. And if you are going to do the hydrolysis in the presence of H2, basically this is, you can call it uh, acid hydrolysis, acid catalyzed hydrolysis. So you can see there will be Markovnikov addition, and in anti-Markovnikov addition, negative part will go to that carbon where hydrogen is lesser, and the rest part will be as. And then you need to pass this through KIO, and there will be oxidizing agent KIO and dilute KOH. So this bond will be broken and it will be oxidized. Oxidized, that means this H will be removed. So this is how. Oh, wait a minute. Yeah. No. Okay. Wait a minute. We need to oxidize this. So how we are going to oxidize this? We are going to remove this hydrogen as well as this hydrogen. So this there will be double bond and then O negative and K positive. This K positive comes from here. This will be basically carboxylic acid salt. Carboxylic acid salt. These questions will be solved easily if your overall concept is clear. Like if you know some concept from alcohol, like this is 2 degree alcohol, 2 degree alcohol, and if you are going to use a very strong oxidizing agent, that means see, first 1 degree alcohol converted into aldehyde, and aldehyde converted into carboxylic acid. 2 degree alcohol, it will be converted into ketone. Okay, and if you are going to use a very strong oxidizing agent, this will be broken and converted into carboxylic acid. Since we are using a base, so this carboxylic acid will be converted into carboxylic acetol, and this alkyl group will be converted into iodide, iodoform. So the answer will be B. Is that clear, Marita? Very good. Krishna, Adriel.
Yes, sir.
Okay, can you change the slide?
Yes, sir.
Yes, sir.
Okay, please do this. You need to tell me the product. This is very easy. Is there any answer? How it can be OH is there? There will not be any OH, I think, because it is alcoholic KOH or NaOH. And in alcoholic NaOH or KOH, beta elimination takes place, if you remember. Right? Marita, aqueous KOH you are going to
Yes,
add.
sir.
So see, this is your alpha carbon, there is beta carbon, and there is beta carbon. So you can you can draw two products. The first one is there is already double bond. So if you are going to remove from here the hydrogen, there will be double bond here and CH3 as it is here. And if you are going to remove from here, this will be the, I think, minor product. This will be the minor